from UET Texla. Today I am going to present our paper titled as Embedded System Design for Real-Time Detection of Asthmatic Diseases Using Lung Sounds in Spectral Domain. Among other authors are Misha Uruj Khan, Ariba Mubin, and Aksa Samar. The contents which I am going to present are as follows: motivation, introduction, literature review, materials and methods, results and discussion, conclusion, and references. One of the chronic diseases in the world is asthmatic illness. In 2016, 339 million patients of this chronic disease have been recorded globally, most of which are children. WHO states that about 4,17,918 asthma patients have died globally per annum, and 24.8 million disabilities are traceable to asthma in 2016. In 2018, Pakistan ranked 47 among the countries where asthma was the leading cause of mortality. The predicted methods for lung disease detection are chest X-ray, magnetic resonance imaging, computed tomography scan. All these methods are costly, require trained specialists, and occupy large space. They also affect a person because they release harmful radiations. Lung sounds come from the lungs when you breathe in and out. These sounds can be heard using a stethoscope or simply when breathing. They can be normal or abnormal. Allergic bronchopulmonary aspergillosis asthma is an infectious disorder that causes aspergillus spores in bronchia to extreme sensitivity. Asthma, recurring lung infiltration, mucoid, and central bronchiectasis are characteristics of this clinical manifestation. Bronchial asthma is a serious chronic illness that swells and narrows the air passages of the lungs. Due to this inflammation, the path of air contains thick mucus, making it difficult to exhale and inhale. The illness is chronic and affects day-to-day work. Both are two of the lethal asthmatic conditions with typical adventitious tones. First paper describes what asthma is and how it can be characterized. It showed that cough and dyspnea are major causes of asthma and they can be characterized into 10 vital types. Identification and classification of 3 lung disease were done in second paper with gray level co-occurrence matrix and extreme learning machine. In third paper, cross-validation technique was used to eliminate common errors. After eliminating incomplete data and selecting 15 suitable features, the random forest method gave the accuracy of 98%. A median filter was used in fourth paper for noise removal from the input image and its enhancement. Deep neural network (DNN) was used to predict asthma severity using data at the national and hospital level. At national level, prediction accuracy was 86% and at the hospital level it was 91.1% on average in the fifth paper. Now we are going to discuss materials methods used for this embedded system. This slide shows the proposed methodology for the detection of asthmatic and non-asthmatic patients. Lung sound data is collected from asthmatic patients such as people suffering from allergic bronchopulmonary aspergillosis and bronchial asthma, gathered from the Pakistan Institute of Medical Sciences Islamabad (PIMS). Non-asthmatic lung sound data was collected from local universities and colleges. During data collection, a doctor was always with us who helped us in identifying whether the person at hand was an asthmatic or non-asthmatic subject. Signal acquisition is performed by keeping an electronic microphone near the left and then right nostrils. The microphone is attached to an amplifier so that amplified signal can be achieved. A random number of samples were collected from subjects. A single subject gave at least a 90-second long signal. The complete embedded system is shown in the figure. In slide shows the complete number of steps and pictures of the data collection setup. We collected the dataset of 3 classes: normal, bronchial asthma, and bronchopulmonary aspergillosis asthma lung sounds by using data collection board. The sampling frequency to store the data as .m4a was 8 kHz, 8 bits and single channel. This figure shows the time domain representation of raw lung sound before preprocessing. The first and crucial stage in data analysis is preprocessing. It consists of removing the bass roll and high frequency disturbances together with other components which can alter the obtained signal. The sound of the heart, muscles and skin are common disruptions. Raw lung sound is normalized to remove amplitude variation. Here, empirical mode decomposition is used for 2 main goals. The first one is to eliminate the noise embedded in the raw signal, and the second one is to extract the area of interest in the signal, which is having maximum discriminative characteristics. This figure shows the empirical mode decomposition of normal, allergic, bronchopulmonary aspergillosis asthma, and bronchial asthma. First subplot of these figures show the normalized lung sound. Second, third, and fourth subplots show IMF1, 2, and 3 respectively. Last subplot shows the residual of normalized lung sound in time domain. In sound processing, the mel-frequency capstrum is a representation of short-term power spectrum of a sound based on linear cosine transform of a log power spectrum on a nonlinear Mel scale of frequency. Gamma tone capstral coefficients is a perceptual modification of MFCC that uses the gamma tone filters. This figure shown here represents the 14 Mel frequency capstral coefficients and 14 gamma tone capstral coefficients of lung sounds which are extracted, making a total of 28 capstral domain features. Relief algorithms sorted the features by their ranks in predicting the outcome of the predictors. MFCC 1 to 5 carried the highest weights, so we trained our classifier on them to get the best possible results. Ensemble Bake Tree is a machine learning meta-algorithm designed to improve the stability and accuracy of machine learning algorithms used in statistical classification and regression. It also reduces variance and helps to avoid overfitting. Now results and discussion. Figure A shows MFCC1 versus MFCC2. Figure B shows MFCC1 versus MFCC3. Figure C shows MFCC1 versus MFCC4. Figure D shows MFCC1 versus MFCC5. Figure E shows MFCC1 versus MFCC6. Figure F shows MFCC1 versus MFCC7. This figure shows the predictor rank importance score versus predictor in relief algorithm. 14 MFCC and 14 GTCC were given to the feature selection algorithm known as relief algorithm. First 5 MFCC got the highest weight, so we used them in classification. We used first 5 MFCCs with the highest weights to train decision trees with 5 different ensemble methods named as ADA boost, bake, subspace discriminant, subspace KNN, and Rust boost. Baked ensemble tree gave the highest average accuracy of 97.4%. This figure shows the confusion matrix of ensemble baked tree. In this research paper, real-time classification of asthma and non-asthma patients is done by using analysis of lung sounds. EMD-EBT-based model is proposed in this paper. This technique is a new approach in field of pulmonology. This embedded system is effective, cost-friendly, and no danger to human health. In this system, we used a non-invasive signal collection technique with no radiation hazards, no training needed to operate this system. This embedded system will revolutionize medical diagnosis of lung diseases. Total samples for normal were 506, for bronchial asthma 319, and for bronchopulmonary aspergillosis asthma 110. Extracted features 14 mel frequency capsular coefficients and 14 gamma tone capsular coefficients of lung sounds are checked through a relief algorithm to see their maximum weights. Using 5 MFCCs selected by relief algorithm are combined with ensemble baked tree classifier. Achieved maximum average accuracy of 97.1% after 10 successive experiments on Raspberry Pi 4.0 Model B. When this system is tested on various cross-validation methods, there is no noticeable improvement in system accuracy. It shows improved device effectiveness even in the 5-fold cross-validation, which decreases the device computation time. Our future aim is to propose a hardware framework for the detection of asthmatic disorder by wheezing sounds. Following are the references of conferences and journal papers used in the literature review. Thank you. Any questions and queries, kindly ask.
Hello everyone, as promised, I will start the new series of paper implementation and the first paper in this series is spectral analysis of lung sounds for classification of asthma and pneumonia wheezing. And here as you can see, when I search this paper on Google, then we will open its relevant IEEE paper. And today we will basically in this series we will see how to implement this paper step by step. And another additional thing that I will be sharing with you guys is its practical deployable GUI, and which you guys can see from here. I will be uploading all the relevant codes, notebooks, and the implemented stuff in this repository. I will also share the link in this YouTube video and the upcoming videos, and I will show you the overall things that we will be going through in this particular paper implementation series. So let me get straight to the deployable part. Yeah, after implementing all the steps and things, you will finally be able to have something like this, a deployable GUI where you can upload and pre-process your own lung sounds, feature models, and then you can get the results on the dashboard. you see here, when you upload lung sounds, you will get something like this. Feature extraction step, it will look like this. And after model evaluation, the trained models that we will deploy in this GUI, you will get the results, and the final results give you the prediction whether it's asthma, pneumonia, and wheezing. And whenever you are either using this paper or implementing it, so do cite this paper in your project reports or even if research publications. Okay, now let's talk about the input data. So this is my private data that I uploaded on my GitHub my Kaggle repository. And if you see this particular data set has three classes: asthma, normal, and pneumonia. As when you will read the paper, you will get to know that an asthma has some relevant audios, asthmatic as wheezing audios, normal have normal human lung sounds, and then in pneumonia obviously we have pneumonia wheezing. Now cut short to, this is the first codebook that I will be explaining to you guys in very detail. So by the end of it, you guys not only have the basic knowledge of how to pre-process or clean a lung sound, but also if you cater any kind of biomedical signal. Okay, now before I touch any code part, I want you to imagine something. Imagine you are a doctor with a stethoscope listening to a patient's chest, and then what do you hear? Breathing, but not just breathing. Sometimes you hear normal airflow, sometimes you hear wheezing, as is the case in asthma. Here you can see, if we simply, I'm just trying to make you understand the concept. And sometimes you have crackling in pneumonia. So when these sounds are recorded with a microphone, they are not clean yet. You get silence, background noise, electric hum, maybe even the patient moving the microphone. So our first job before we do any machine learning project or any machine learning implementation is to clean and prepare those signals. And this is what preprocessing means. And we will do this in 3 careful steps here. Now let's start seeing the node. So the first one is the normalization. We make sure loud and soft recordings are treated equally. And in filtration, we will be keeping only the frequency band that contains lung sounds. And in segmentation, we will be chopping the 30-second, 20-second, or whatever long recording you have into smaller meaningful chunks. By the end of this lecture, you will see why preprocessing is not optional. It's the foundation of everything. And here I simply explained the relevant libraries and why do we need them, and some of the global parameters that will stay the same. Okay, so first what we do, whatever, as this is a private dataset, what you can do is that you can either use open source datasets which have relevant pneumonia, asthma, and normal lung sounds and make their folders, and then simply by taking this code you can pass your folder path in this particular spot and you will have your data loaded. And in this particular case, the sampling rate of the audios is 44.1 kHz, and we are particularly focusing to by filtering when I mentioned the filtering part. So this is the exactly limit that we will be setting, and I will also explain it further. Okay, So let's start by loading one of the audio files. There are .wav files recorded at a sampling frequency of 44.1 kHz. That means every second of lung sound is represented by 44,100 numbers. Think of it like a movie camera. A camera captures 30 frames per second, and an audio recorder captures 44,000 frames per second. That's how detailed the sound is. And by loading the audio, how do you do that? You basically, if you conventionally just want to show or load a single audio file, what you do is that you load a librosa file, basically the librosa library, and then you pass your path and your obviously wherever your recording is. So here you can see that we have the path sampling rate we have fixed, and by giving the pass we are making sure that the sampling rate is equal to what we have fixed. And then we are basically centering the data bias to avoid DC bias before band pass, and then we are applying band pass filter, and then after band pass filter we are applying zero phase filtering. And normalization after filtering for later features extraction is optional. Either you can do it here or you can do above this. At this stage, let's talk about a raw signal. And if we see one of the raw signals, which I will show you in this particular paper, if you see raw signals here, the raw signals, they look messy. It's raw, pressure values, sometimes strong, sometimes silent, and we need to fix that. And why do we need that? Because different recordings can be loud or soft. Why? Because maybe the microphone was close to the chest, maybe the patient spoke softly, maybe the environment was noisy, and if we don't normalize, the model might think a loud asthma sound is different from a soft asthma sound. And actually, both are the same disease. So we normalize in two steps. We subtract the mean to center the signal zero around and divide by the maximum amplitude to scale through -1 and 1. Here, as in this particular formula, you can see. And now if we go to the code, we can see that we have implemented this part here. This min max normalize function is doing that. Now all recordings, no matter how loud or soft, after passing through this min max normalize function, they will be equalized. This ensures that when we later calculate features like spectral energy, it reflects the breathing pattern, not the microphone volume. Simply, this is like adjusting the volume knob on every recording so they all start at the same level. Okay, now the next step is filtration. As I mentioned earlier, that I will make you go through this filtering step. So now, how do we, why exactly are we using, why do we need a filter? Imagine you are listening with a stethoscope. Do you care about the sounds of the patient's heart? Not really. In this particular case, you want lung sounds, and what you care about are high-pitched noise from the microphone. No, you want lung sounds here. And after doing detailed literature review, we came to know that lung sounds are concentrated between either 150 or 250 Hz to 2000 Hz, and below 150 Hz is mostly heartbeats, body movements, and electric hum. And above 2000 Hz is microphone hiss and noise. So we built a filter that passes only that range, like tuning your radio to the correct frequency. We use a 10th order Butterworth filter. Why Butterworth? Because it has a flat pass band, meaning it doesn't distort the lung sounds. And here, if you see, this particular code builds a filter and applies this. And obviously the result will be the clean version of the lung sound. And here, if you see the range, there is F low and F high, and we can see that earlier we have defined basically this. We have basically defined the exact part, like 250 to 2000 Hz. That will be the F low and F high. And what does this mean in practice? Wheezes, crackles, bronchial breathing, all preserved heartbeats, microphones, his background noise cone. This is why filtering is essential. Now, the third part is segmentation. And by segmentation means cut the signal into frames. Let's go to the segmentation part. This here is defining the kind of segmentation we will be doing. Now let's understand it. Because lung sounds are non-stationary, that means their properties change with time. A wheeze may last half a second, a crackle may last 1000 milliseconds. If we analyze the whole 30 seconds at once, we miss these fine details. So we divide the signal into 0.25 second frames. Now earlier I mentioned the total signal has 44,000, and if we try to find the 0.25 second frames of that, we will have 11,025 samples with obviously 50% of overlap, which as I mentioned here, so nothing is lost. And this code will give us exactly 239 frames. But wait, many frames are also silence, and silence has no medical meaning. If we feed silence into the classifier, it will confuse the model. So what we do is we calculate frame energy and remove low energy frames by using these two, these short time energy and drop silence frames. After silence removal, only 191 frames remain. That's 80% useful signal and 20% silence removed. This way, the model learns only from meaningful lung sounds. Okay, so this is how I visually call, and you can see that the Butterworth's 10th order band pass filter that we designed is only passing the frequency range that we defined earlier. Now let's see the results. This is the code. Basically, if you only want to reprocess a single lung sound, you apply all the steps, and then when you see it, this is here something that will look like this, and I will giving you the example of this particular one. So let's try to understand it. The fs is the sampling rate of the recording audio, and x raw here is the raw waveform that had 1.32 million samples, which was basically exactly 230 seconds of the recording. And x centered, when we subtracted the mean, so the signal oscillates around the 0, and this is the shape of that. Obviously we have normalized the data, so the shape is exactly the same, and xvp is representing the bandpass filtering, and these are the frames. The audio we split into 239 frames, and each is 0.25 second long, and the frames that we kept are 191 after silence removal, and that proves that we kept 80% of them. So instead of what all this preprocessing step proves is that instead of one long messy signal, we now have a short manageable chunks of meaningful sound. Imagine a novel. Instead of reading all 5,000 pages at once, we break it into chapters. And chapters here represent frames, but skip the blank pages, and blank pages are that of silence. Now, if we visualize all three lung sounds, normal, asthma, and pneumonia, and we make it go through all the pre-processing steps that we defined earlier, then we would have something look like this. So all these three, basically this signal is showing the pre-processed signal. Here it is quite visual. If you see it, I will zoom it. Okay. And now here if you see, the normal signal show bursts of airflow. Asthma looks too weak, often irregular, and pneumonia looks flatter with some strong patterns in between. And this already shows that preprocessing is making disease patterns quite visible. And if you see the frequency domain, normal shows strong low frequency components, while asthma shows spread energy more widely. That's why, because wheezing sounds are musical and wheezes create strong frequencies, while pneumonia as compared to is weaker with suppressed high energy. So we can clearly see the difference. That is why preprocessing is not just cleaning, it's revealing the medical truth hidden in the signal. So if we simply summarize this, what we did was we normalized the signals to equalize volume. Then we applied a Butterworth bandpass filter to keep 250 to 2000 Hz. Then we segmented into frames and removed silence. We also visualized time domain and frequency domain signals of preprocessed audios to see that all the preprocessing steps are taken correctly. And this preprocessing pipeline ensures that the raw sound is transformed into a clean, structured input ready for picture extraction in Notebook 2. So in the next lecture, we will calculate spectral features that describe the shape of these lung sounds mathematically. Thank you, and remember, preprocessing may seem boring, but it's the most critical step, and without it, everything else falls apart. And all the links and details will be shared in the link below. If you like this video, do comment and subscribe. Bye. Welcome back everyone. In the last lecture, we cleaned our lung sound recordings using preprocessing. Remember, we normalized, filtered, and segmented. Now our sounds are ready, but cleaning alone is not enough. A computer cannot hear wheeze or crackle the way a doctor or a human can. And computers don't understand sound waves like humans do. What computers do understand are numbers. So, in this particular lecture, we will convert our signals into features. This is the Kaggle repository that I created for you guys so that I can share my codes publicly. And in this one, we will be going through the second spectral feature extraction. Okay, so when I say the word feature, what does come to your mind? Features are basically measurable properties that describe sound or any data that you have in your hand. For example, if you want to describe a human face, you don't give the whole photo. You give measurements, nose length, eye distance, and jaw shape. Similarly, to describe a lung sound, we don't give the whole waveform. We extract key features. Like here we mentioned, for example, spectral centroid, spectral crust, or spectral spread. These features basically capture the fingerprint of each disease. By the end of today's lecture, you will see how asthma, pneumonia, and normal breathing separate in the feature space. Okay, as you can see, first we inputted all the relevant libraries. Then we defined the path of where all the three folders that contain the lung sounds of normal asthma and pneumonia are present. Then obviously we will simply here first repeat the steps that we did in the first notebook. We will read all the audios. Then we will apply this normalization. We will frame our signal into smaller segments, and then we will obviously try to remove silence and drop the silence parts. And this is basically the Butterworth's 10th order bandpass filter. Now let's come to the main feature extraction function. Our sounds are in the time domain after preprocessing, but many patterns are still hidden. When during our discussion with doctors, they said that wheezing is high-pitched and pneumonia crackles are burst-like. And what they defined are not time domain properties. In order to get high-pitched and burst-like characteristics, we actually need to transform our signal into the spectral domain. And for that particular, we extracted 9 features. Formulas are defined here. Okay, let's for example take spectral centroid. What is it? Spectral centroid is often called the center of mass of the spectrum. Imagine balancing the spectrum on a seesaw. Where would it balance? That's the centroid. High centroid is equivalent to bright, sharp, wheezy sound, and low centroid is equal to dull, deep, normal breathing sounds. So, in this case of lung sounds, normal breathing is equivalent to lower centroid. Asthma wheeze is equal to higher centroid, and pneumonia wheeze is scattered but often shifted. And when we extract spectral centroids, we see that asthma points clusters at higher centroid values, That's why, because asthma sounds more musical, it has more wheezing-like pattern. If you go to spectral crust, so basically spectral crust measures how peaky the spectrum is. If one frequency dominates, crust is high. If energy spread, crust is low. Think of it as like a choir. If one person screams, crust is high. If everyone sings together, crust is low. Asthma often has strong single frequency wheezes and high crust, normal breathing spreads, energy and lower crust. Now if you look at spectral entropy. So what does entropy generally means? Entropy means disorder. And spectral entropy particularly measures how random the spectrum is. If the energy is spread evenly, then it has high entropy. If it is concentrated in a few frequencies, then it has low entropy. Usually, normal lung sounds are more structured and have lower entropy, while asthma, because it contains wheezes, has spreads energy-like pattern and thus has higher pattern. Spectral flux. Flux mean change. Spectral flux measures how much the spectrum changes between frames. Stable sound and low flux, rapid changing sound and high flux, asthma wheeze, stable tone and lower flux, while pneumonia crackles or wheezes have sudden bursts and thus have higher flux. Spectral roll-off. Roll-off is the frequency below which 85% of total energy lies. It's like asking how far into the spectrum must we go to capture most of the energy. Normal breathing energy is low frequency and has low roll-off. While asthma, it pushes energy higher and thus have higher roll-off. Okay, now I have briefly explained you all the features. Now what in this code we will be doing is that we will preprocess our signals. Then obviously on all the frames, all the good frames, we will extract the features. And if you see how the extracted feature looks like, they are some kind of number. And let's say this is the main audio sound, and then as we segmented into 250 millisecond frames, for that particular part we try to extract the features. And features are what? Features are like a toned down version and a toned down number that is representing some kind of characteristic. And as we need to train our machine learning models, what we did is we simply saved all the extracted features of all the lung sounds into one Excel file in this particular form, where you have all the features, their values, what class it belongs to, and what was the main file name. Now let's visualize these features. Let's see the first graph, spectral centroid versus spectral crust. Look at this scatter plot. Each dot is a frame of lung sound. Blue is representing normal, red is representing asthma, and green is representing pneumonia. On the x-axis is centroid, the brightness that shows the brightness. And on the y-axis is crust, and crust is like the peakiness of the data. So what do we see here? Asthma dots that are red in color cluster high up, meaning wheeze sounds are dominated by short peaks, and normal dots that are blue are spread lower, meaning they have more energy. While if you see pneumonia, it is mixed but tends towards higher crust at lower centroid. This makes sense. Why? Because wheezes are pure high tones and pneumonia has wheeze/crackle, has burst, and they're normalized. So they look equalized in this one. If we see spectral centroid versus spectral entropy. Now entropy. Here we see that asthma dots spread across high entropy values. Why? Because wheezes distribute energy unevenly, increasing randomness, while normal lung sound has higher entropy and breathing is structured, and pneumonia sits in the middle but still shows more variation. This confirms that entropy is a good marker to separate asthma for normal and pneumonia lung sounds. Now moving on to the next one. If we see spectral centroid versus flux. Flux is how much the spectrum changes from frame to frame. So you notice pneumonia, that is green in color, is very spread, while crackles are irregular, so flux is high. Normal and asthma are flatter, while asthma wheeze is a steady tone, so flux is lower. Flux captures crackle-like disease. Spectral centroid versus roll-off. Here we compare centroid with roll-off, and the pattern is, again, asthma shifts to higher values, wheezes push more energy to higher frequencies, normal stays lower, and pneumonia is scattered but mostly low roll-off because bursts don't push energy far up the spectrum. This tells us roll-off is the most useful of distinguishing asthma. Feature correlation heat maps. So basically, heat maps give us a visual overview of how strongly different features are related. We have +1 that shows that feature moves together and they are highly redundant. Then we have -1 that shows that features move in opposite direction. And 0, it shows that there is no strong relationship. All the ones are independent. So now let's compare all features. Do they overlap or are they independent? If we see, this is how a correlation heat map of all classes put together look like. Red means strong correlation, blue means weak. For example, centroid and entropy are strongly correlated. They rise together, but flux is more independent. It gives us new information. Now we split it by class. If you see the normal one, the correlations differ by disease. And normal has a more structured pattern that shows that the features follow each other in it. Now if you look at the correlation map of asthma, in asthma you see that entropy and roll-off, they are quite tightly linked together. And if you see the feature correlation map of pneumonia, here flux and spread play a bigger role. This shows each disease has a unique feature signature, and that is what and how our machine learning model gets to differentiate between these different classes. So what did we learn today? Let's summarize. We moved from time domain to frequency domain. In frequency domain, we particularly focused on spectral features. We basically extracted 9 spectral features. We visualized how each feature separates disease. We also analyzed how feature correlations look like per class. These features are like the numerical fingerprint of lung disease. In the next lecture, we will feed these features into classifiers, logistic regression, or KNN or SVM, and we will see how each model will diagnose asthma, pneumonia, and normal breathing. Remember, today we gave the computer ears. Tomorrow we will give it a brain. And in the last, I will show you the complete Excel file of the extracted features that we will be feeding our classifiers in. In here you can see that it's quite an elaborative one. Let's go to the last. So we have this asthma, all the asthma features. Then we have normal, and then we have pneumonia, and we have total 21,258 extracted features from our dataset. If you like this video, do subscribe, and if you have any query or confusion, do let me know in the comment section. I will also be sharing all the relevant codes in the description below. And do subscribe. Bye. The goal of today's notebook, or should I say the lecture, is to perform classification. In the last notebook, we turned audio into features. I will show you the Excel file that has all the extracted features. So basically today we will feed this Excel file into our models. That means that today we give the computer our decision making brain. We will load a feature table as shown, then we will split it into train test. We will fit multiple models. We will evaluate with accuracy, precision, recall, F1, and visualize confusion matrices, and finish with a McNamara significant test to check if a model is truly better, not just lucky on this split. So first, what we do is load our features file. The Excel file is a row per frame or aggregated window with columns like SCN, SCR, etc. plus a class label. Now basically what we do is we separate our features from our labels. X now is the numeric feature matrix and Y is the label vector. Then again what we do is that we train and split test features. Here you can see that we are training on 70% of the data and we will be testing on 30% of the extracted features. And then comes our models, machine learning models. So I will simply briefly give you an overview of each of the model. What does linear discriminant analysis do? It draws a straight line that is a hyperplane between different classes, and it is fast and interpretable as compared to other models. If we look at the KNB, it basically applies Bayes rule per feature. And what is surprising is that it actually does quite good on noisy data. If we look at the decision tree model, that is the fine tree, it will define rules like if spectral centroid is greater than 900 and flux is greater than 2000, then it is asthma. It basically tries to define rules like such. Then we have find canon. So what this particular canon does, it picks the nearest neighbor. It is very sensitive and it has high variance, but it can be great when features are very informative. If we look at subspace canon, it's mentioned here, it is actually a smoother version and gives vote basically nearby points, vote gets more preference. Now about the bagging tree, many trees on bootstrap samples. So basically it has many trees on bootstrap samples and average predictions and lower variance. So typically it is also quite strong. And then we have different versions of support vector machine, which for the time being I have commented out. So first of all is accuracy. Accuracy is the overall fraction correct. Thus, how accurate your model is performing on all over your data. But it can be quite misleading under if it is imbalanced data. Precision is the average of per class. When I say asthma, how often am I right? So this is what precision will be telling us. Recall is the average of per class sensitivity, meaning when I say when the case is asthma, how often do I catch it? It is recall. And F1 is the harmonic mean of precision and recall per class. Then it is averaged, and if balance misses versus false alarms. Then we are also computing type 1 and type 2 error per class. Let me explain what type 1 and type 2 errors are. Type 1 is basically false positive rate. How often we raise a false alarm for each class. Type 2 false negative rate. How often we miss the class. And if we see it from medical lens, missing pneumonia. So here pneumonia is false negative and missing pneumonia can be dangerous. So we need to keep type 2 low. Overcalling asthma is false positive. We also need to keep it low. Why? Because if it is high, then our type 1 would be high. And then obviously we are showing the confusion matrix report, which will give us the overall view of each one. Let's look at the result. What happens if we feed our Excel file and train our models on them? As I mentioned earlier, we divided 70% of data to be fed into the models as training data and the rest 30% as testing. So 70% of data is equivalent to 14,000 samples and the rest of the 30% data is equal to 6,000 samples. Why is this important? The training set teaches the models and the test set, which the model never sees during training, tells us how well the model generalizes to unseen lung sound data. So everything you see from now on is true generalization performance, not just the memorization of each model. In particular case, let's look at the linear discriminant analysis, linear discriminant model. And as defined earlier, linear discriminant is a linear classifier. It tries to separate classes with straight lines in feature space. And if we see the confusion matrix here, it predicts asthma very strongly. 2000, so 2900 something samples are exactly identified asthma as asthma, but it struggles with normal because many normal cases get misclassified as asthma. Pneumonia is also partly confused with asthma. So the general interpretation would be asthma dominates because its spectral features may align more strongly with the linear separation, but the real-world diseases are non-linear, which is why linear discriminant underperforms. If we talk about kernel naive bias, this looks very different. Why? Because KNP heavily misclassifies many asthma patients and predict them as normal. Normal also gets confused with asthma. Why is it behaving like this? Because naive bias assumes all features are independent, but our lung sounds features are highly correlated. Remember the previously plotted heat maps? That assumption breaks down, so KNP struggles. Pine tree. Now this is impressive. Nearly all asthma cases are correct. Normal 1283 are exactly correct. The pneumonia 1357 are again exactly correct. Also well separated. And we see very few off-diagonal errors. Why is it behaving so good? Because Decier trees partition the feature spaces into flexible regions. Our spectral features, that is centroid, entropy, roll-off, are non-linear and threshold-like, and trees are perfectly suited for them. That's why pine tree is emerging as the best model so far. Gaussian naive bias. This is basically the same pattern as KNB. It has strong overlap between classes, many asthma and normal classifications. Again, because of feature correlation, Gaussian MB not just cannot handle the complex relationship in lung sound features. Fine Canon. Here's Canon with just one neighbor. Asthma classification is again quite strong. Normal and pneumonia are decent but weaker. But still it outperformed naive bias. Why? Because Canon works by looking around in the feature space. With fine Canon, k is equal to 1. It memorizes training examples. This helps in cases like ours where disease cluster tightly. And the downside is noisy samples can mislead it. That's why the error remains. Back trees. Back trees combine many decision trees. An ensemble. This is even cleaner than pine tree. Why? Because ensembles reduce variance, where a single tree might overfit bagging averages across 50 trees. That stabilizes predictions. This is why BT rivals are even beats FT. Subspace Canon. This variation of Canon-based distances and uses multiple features, subspaces. Performance is better than fine Canon, but not as good as trees. It captures more global structure, but still struggles with overlapping disease features. Canon is in the middle ground. Here's the summary table with accuracy, precision, recall, and F1. If we see this particular table, we can see each model's ranking. Linear discriminant, the accuracy is almost 0.63. It is an average model. If we look at KNB and GNB, both have around 43% accuracy, which is very poor. Then again we have pine tree. Its accuracy is 0.97, which is quite understanding. 0.975 actually, so around about 98 you can say. And BT accuracy is exactly 98.22 in middle of 98 to 95%, and SKNN accuracy and FKNN, both of them are 85. Good but not perfect. So overall, if you see that FT and BT stand out as winners. Now if we look at the accuracy bar chart, models shoot up near the top, that is FT and BT. Naive Bayes variants lag behind, while KNN sits in the middle. So this visually instantly tells us which models are reliable. Accuracy alone can be misleading if classes are imbalanced. That is why F1 score is critical. Here again, FT and BT dominate. FKNN and SKNN are decent. LT is moderate and naive Bayes is poor. So across both accuracy and F1, FT and BT are the consistent leaders. Now let's see the statistical significance with Neckmar's test. High accuracy alone doesn't guarantee that one model is truly better than another. So to test whether the difference in performance is statistically significant and it's not just a random choice, we will use Neckmar's test. So basically how it works, we compare each classifier directly against the best variant. In here we have FT and BT, and we will be basically counting two variables. One, that our case's competitor is correct but FT is wrong, and the second is that the model that is performing the highest is correct but competitor is wrong. So if both variables and both models perform similarly, both variables would be equivalent. And if the models are statistically different, then the values of B and C would differ significantly. So this is how we perform Neckmar's testing. And here are the results. So don't mind there, here basically we are competing actually against the FT, not SCM. And let's summarize everything. So naive Bayes, both KNP and GNP, they perform poorly. And if we see LD versus FT, it gives us a significant difference. KNP versus FT, again significant. GNP versus FT, significant difference. FKNN versus FT, again significant. But BT versus FT, because both of them as previously have around about 98% accuracy, have significant, but the p value is 0.000011, and this is the closest competitor. So FT basically the strongest model, but BT come close. So that's how FT is the ultimate winner. Now let's just visually see that whether which one is significant or not, and how our tests are performing. And we are only able to get a very good strong p-value against BT. But yes, they are competing again, and the rest of them are not quite good. Now let's just summarize. We train multiple models, and among them naive Bayes, both KNP and GNP, they perform poorly. So here they are weak models. The moderate models are linear discriminant, FKN and SKN. They are okay, but they are not giving us state-of-the-art accuracy. Now the strong models are FT and BT because they both dominate accuracy in F1. And in significant testing, FT significantly outperform all others, while BT has the closest rival. So if we had to pick a single classifier for deployment on lung sound analysis, FT, that is fine tree, would be our choice. And that concludes our deep dive into the classification results. So this experiment basically shows how machine learning plus signal processing can provide meaningful insights for biomedical applications. now have a complete workflow: pre-processing, feature extraction, and classification. And as I told earlier, in the next stage we can explore the deployment, turning these trained models into an application or a clinical tool. And we will also deep dive into deep learning models for automatic feature extraction. Any confusion or any queries regarding the code implementation or any step that you are not exactly able to understand, so do comment, and I will also share the link of this notebook. Do subscribe. You have to go, as I will be uploading the next one very soon. Bye. Hello everyone, this is Engineer Misha Rujhan, Chairperson Community of Research and Development, CRD. And basically, today we will go through this IEEE conference paper that is published, and its title is Spectral Analysis of Lung Sounds for Asthma and Pneumonia Wheezing. Well, have you ever listened to someone breathe and heard a faint whistle or wheeze? Most of us ignore it. But what if I told you that simple sound could be the difference between life and death? And as you can see the figures mentioned in this introduction paper here, these. Every year, asthma and pneumonia claim millions of lives. And according to World Health Organization, as you can see also here, 235 million people and more than 3 million people died every year. And pneumonia, often called a silent killer, also continues to devastate families around the world. Now, here is the question: what if we could diagnose these deadly diseases just by listening to the lungs? No expensive CT scans, no bulky MRI machines, just the power of sound and artificial intelligence. And in today's video, I'm going to take you on a fascinating journey inside my this IEEE published paper, where basically we used spectral analysis of lung sounds to classify asthma and pneumonia with stunning accuracy, and how this could change healthcare forever. Okay, now the question is, well, why does this even matter? Right now, diagnosing lung disease usually requires expensive equipment or highly trained specialists. Chest x-ray, CT scans, and even invasive procedures like bronchoscopy are common. But these methods are costly, they are time consuming, and simply unavailable in many rural hospitals or developing countries. Imagine a village doctor with just a laptop and a small microphone being able to instantly detect asthma or pneumonia. Well, that's the dream we are chasing, and in our research, we have come very close. I will, the main question that would come to anyone reading this paper is, what's the science of lung sounds? Well, if I will simply break it to you. Let's talk about lung sounds. When you inhale and exhale, air flows through your lungs. If your airways are clear and healthy, the sound is smooth. But when the airways narrow or become inflamed, they produce usual sounds called wheezes. These wheezes are high pitched whistles that can occur during breathing in or breathing out. In asthma, wheezing happens because mucus and swelling block the airways. And in pneumonia, the alveoli, the tiny air sacs in the lungs, they get filled with fluid, making breathing extremely difficult. And because doctors, they are medical professionals, they are trained to detect these sounds with a stethoscope. But here's the catch: to really distinguish between asthma wheeze and pneumonia wheeze and normal lung sounds or breathing, it takes years of expertise. What if we could teach a computer to listen, analyze, and classify these sounds with almost perfect accuracy? That's exactly what we set out to do. if we particularly look into the data acquisition, well, this is the literature review, some of the previous work that people did. You can, well, I will share the link in the description. You can go through it and you can learn about that too. Now let's come to the main part. What's data collection? How do you collect a lung sound? Well, to build our system, we first needed real data. I will simply just amplify this figure to show you this. To build our system, basically, we first needed real data. And how do we collect lung sound recordings from 300 subjects? Mm, Obviously, we have to find patients, and after finding those patients, we did these recordings at PIMS Institute in Islamabad after proper ethical approvals. And what we did was we used an electronic microphone, a stethoscope placed either near the nostril or on the chest to capture the sounds, and each patient contributed multiple samples, and each one of them lasting about 10 seconds. And this gave us a large data set of over 3,000 recordings, and this was a raw material, the lung symphony of human body waiting to be decoded. Now the next big question is, your raw lung sounds are messy. Actually, they are super messy, and they include, I will show you, I will simply show you uh, a raw recorded signal of three of our focused categories. In here you can see this particular one. I will show you this figure. Time domain representation of lung sounds before preprocessing. Now they include silence, background noise, even heartbeat, because in your human body, your lung sound is exactly like close to your heart, so you get heartbeats. To make sense of it, we had to clean the data using three steps: normalization, segmentation, and filtering. Okay, so what does normalization mean? And this is basically the formula. You can read all the jargon, but I will simply explain. Normalization means adjusting the sound levels so that everything is on the same scale. Imagine adjusting the volume so one sample is not louder than other. It's simply as that, and its mathematical formula is given here. Now the next one is segmentation. Simply put, segmentation means chopping the sound into small frames, and that frame is selected by you, and here we basically selected 250 millisecond frames, so we could isolate the parts with actual breathing and discard the silent portions. And obviously, finally, the big question, as we told you, the hard sounds. There are also hard sounds in lung sounds, so how do we filter that? So there are special signal processing techniques called as filters, and one of them is bandpass filter. And here specifically we used a 10th order Butterworth bandpass filter to keep only the important frequencies between 250 and 2000 Hz. And why particular this frequency? Because that's where the wheezing magic happens, and anything outside this frequency region, is just would, in this particular case, would be just noise for us. Okay, now that we have, I will show you the cleaned version, and here you can clearly see the difference between before and after. If you see the green ones, the lesser parts, these, the big one overlaps, they were noise, and now they are filtered out. And in the pneumonia ones, the bulky, the overspacious ones, it's also. And in normal, and why? Because a normal is visually looking very quite different from others, because usually when you are ill, your lungs, obviously, they don't have that much power, and when you output that and when you map that analog signal to digital one, obviously it's not as healthier and as strong as a normal person lung sound signal would be, as here you can see that. let's turn these sounds into data, and in particular if we talk about feature extraction. Okay, now came the fun part, feature extraction. Well, think of this is as teaching the computer what to listen for instead of just handing it raw sounds. We converted the sounds into numbers that describe their characteristics. For example, here if you see spectral centroid, we made the spectral centroid, and simply put, it tells us the gravity of the sound. What's the center of gravity of the sound is, and the mathematical formula to calculate is given below. And if we talk about spectral flux, which is below, I'm just randomly explaining you these features. The details you can obviously, when I will share the paper, you can see. And if we talk about spectral flux, well, it means how quickly the sound changes between frames. Well, basically the difference between a steady whistle and a fluctuating one. And if you talk about just spectral entropy, and where is our spectral entropy? So basically here is the spectral entropy, and spectral entropy tells us how chaotic or ordered your sound is or your signal is. And if you talk about spectral roll off, which is here the seventh one, so it basically identifies the point where most of the sound energy lies. In total, we extracted 9 features. To put it simply, these features are like musical fingerprints of the lung sounds. Just as Spotify can identify a song by its unique waveform, this particular system, or you can say this particular trained AI methodology, could identify whether a sound came from a healthy lung or an asthmatic lung or a pneumonia infected lung. And now the AI brain classification. Once we have the features, it's time to classify them. We tested several machine learning algorithms, and the tested ones are listed here. You can read them yourself, as you must be familiar by them, but I will simply explain the superstar of our show, that was support vector machine. If you have never heard of SVM, well, imagine drawing invisible boundaries between different group of points on a graph, and SVM finds the best boundary that separates the categories, in our case asthma, pneumonia, normal, and we ran the system. The results were jaw-dropping. Linear SVM achieved an accuracy of 96.7%. That means the computer was right nearly 97 times out of 100 in classifying the lung sounds correctly. Even when we cross-validated the system with different test bits, the accuracy stayed rock solid. This is better than many conventional diagnostic methods, and it costs a fraction of the price. Okay, the main question is, why is this revolutionary? Why? Is this so groundbreaking? Because it democratizes the healthcare. Expensive medical machines are privilege of big hospitals, but microphones and laptops are everywhere. Imagine deploying this system in rural clinics, refugee camps, or underfunded hospitals. A nurse or a paramedic could record a patient's breathing, and the AI could instantly tell whether it's asthma, pneumonia, or normal. And early detection means early treatment. That could save millions of lives every year. And basically, these are some of the scatter plots of the extracted features. These are all of this is telling the spectral features of lung sounds, scatter plots, some of the results. These are the, this is basically linear SVM, the top gunman cubic, and the rest of them. And these are the other machine learning algorithms. And here is the confused matrix of the best performing classifier. So now, what's the future of AI and lung diagnosis? Well, this particular research focused on asthma and pneumonia, but this is just the beginning. The same approach could be expanded to detect other lung conditions like chronic obstructive pulmonary disease, the short form is COPD, tuberculosis, and even post COVID complications, or if any other apocalyptic uh, virus like COVID comes, God forbid. We could also integrate it into wearable devices like smart patches or chest straps that continuously monitor your breathing and alert you if something goes wrong. And here's the most exciting part. Imagine your smartphone becoming a mini doctor. With just an app in your phone's microphone, it could analyze your breath or lung sound while you sleep and notify you if early signs of pneumonia are detected or whatever. That's the kind of future this research points towards. And that's all. Well, let's just recap. And so let me take you to the main figure of the proposed system. Yeah, here this is. So we started with a deadly global problem, asthma and pneumonia. We listened to the hidden music of the lungs. We cleaned the signals, extracted their unique features, and trained an AI to classify them. And with this particular system, we achieved an incredible 96.7% accuracy in detecting disease from sounds alone. This research proves many things, but one of them is sound is more powerful than we think. It carries the secrets of our health. And with AI, we now have the tools to unlock them. Now, I want to hear from you. Do you think AI driven stethoscopes will actually replace traditional diagnosis? Could this be the key to affordable healthcare for all? Let me know your thoughts in the comments below. And if this blew your mind, make sure to hit that like button, share this video, and subscribe because together we are spreading not just knowledge but the sound of science. And I will tell you an exciting news after receiving many of the comments uh, to share the codes of the published papers. This will be the first series that I will start sharing the code of the papers in either MATLAB or Python their Python implementation. And I will not only share the explanation videos, step by step explanation videos of the